Hello everyone. In this video, we are going to find out about how to transform a random variable. So let's say I have a random variable x and I have been given its probability density function, or let's say I've been given its cumulative distribution function, and I want to calculate another random variable which is a function of f. So let's say I would have a random variable x here and I have a random variable y which is a function of x. So how do I calculate the density function and the distribution of this random variable y? Let's find out in this video on how to solve these problems. Now, let's say I have a random variable x and I have been given its probability density function, which is represented in this way as small f of x, and let's say its probability density function is this. So it increases from the values of x equals 0 to small 1 linearly like this, and then it stays constant at the value of 1 from the values 1 to 1.5. Okay, now let's say I have a random variable y which is a function of x and I have to find out its probability density function. How would I go about it? Okay, so let's see. We define a random variable y which is equal to 2 times of x. Now, in order to start solving this problem, first we need to analyze the random variable x in depth. So we need to find out its probability density function as well as its cumulative distribution function. So let's start by finding out the cumulative distribution function of f. CDF of x. Let's find this out. Now, you know that the cumulative distribution function of x is the integral of the probability density function of a random variable. Now, let's calculate the cumulative distribution function of this. So we integrate x from, let's say I take the range of x from 0 to 1. What would the cumulative distribution function be like? So I integrate this value x dx from, let's say, the value 0 to k, where k lies between 0 and 1. So this would be x square by 2, 0 to k, which is k square by 2. Okay, so this behaves in a quadratic manner. So you can say that by this, let's say if small k is some value x, so this would behave like x square by 2 from the range 0 to 1. I also forgot a integration constant c. So let's say I have this value c. Now we know that there was no density of this random variable before the value 0. That means fx of 0 was 0 and fx of any negative number is 0. So if I put in the value of 0 and here the value should be come out to be 0. So that means c plus 0 equals 0. Hence c equals 0. So this means the cumulative distribution function will be this from the range 0 to 1. Now let's see its behavior in the range where small x varies from 1 to 1.5. So here it's 1 times dx, which goes from 1 to, let's say, some value k. Okay, so this would be k minus 1 plus c, the integration constant. Now let's see what this value would be like. Now we also know that there is no density after the value of 1.5 because the PDF is 0. So this means that cumulative distribution function at value 1.5 would be 1, and any value above 1.5, this value of cumulative distribution function would be 1. So let's say I put in the integration constant as some value here. So we know that if k equals 1.5, it would be c plus 1 0.5 equals 1, hence c is equal to minus 0.5. So if I just plug in this value here, I would get the value as k minus half. Now for any value, let's say k equals small x, this function would behave like this: x minus half from the range 1 to 1.5. Let's also map it in graph. So this is 1, this is 1.5. It increases in a quadratic way like this till it reaches the value half, and then it starts increasing linearly till it reaches the value 1, and from this point onwards its value would be constant as 1. So this is how the CDF of x looks like, where this portion is x by 2, sorry, x minus half, and this function is x square by 2. Okay, now that we have found out the cumulative distribution function of x, you can also write fx as this. So cumulative distribution function of x is all the probability of a random variable mapping a value less than small x, like this. So in the next step we will find out the cumulative distribution function of y. So let's denote it in this way. Let's break it into piecewise steps. So in the first step we find out CDF of x, then we find out CDF of y, and in the third step we find out the probability density function of y. So we'll follow this manner. Now to calculate CDF of y, we know that we have to calculate Fy of small y, which is this P of y less than small y. Now how to convert this function to be like this function? Let's see. So we know that f of y, which is the CDF of y, looks like this. So here I will replace the value of this random variable capital Y as 2 times the value of this random variable x, capital X, as we see that this random variable was defined in such a way. Now this is less than small y. You can also transform it and write it in this way: P of x less than y by 2. Now that you have written it in this way, you can draw parallels with our cumulative distribution function of x, which looked like this, which was f of x. Now we know that the cumulative distribution function of x is a piecewise function which looks like this. So here we have got two ranges, the value of small x being from 0 to 1 and the value of small x being 1 to 1.5. So let's do the transformation. So here we would need to replace this by y by 2. So if x is, let's say, less than equal to 1 and greater than equal to 0, that means the equivalent range for y would be this. So y would be in between the range 0 to 2, and for the range where x lies between 1 to 1.5, the y would lie between this range. So y would lie between 2 and 3. So you can then calculate Fy of small y, which is P of y less than small y. You can also write it in this way: p of x less than equal to small y by 2. And let's say for the first range, for y lying between 0 and 2, what would be the value of the CDF of y? It would be, since it follows the pattern x square by 2, if you just replace y by 2 here instead of x, so it would be y by 2 square divided by 2, which would be y square by 8. So this value would be y square by 8. And for the range where y lies between 2 to 3, its behavior would be similar to x minus half. So if you just plug in the value y by 2 here, so it would be y by 2 minus half. For y between 1 to 3. Okay. So we have seen that this is the cumulative distribution function of y. We can also plot it on a graph like this. So this is small y and this is the CDF of y. It starts from 0 and increases in a quadratic manner till the value of 2, and if you just plug in the value of 2 here, it would be 2 square by 8, which is half. So this value would be half, and then it will increase linearly till the value 3 with a slope of half. And this value would be 1, as if you plug in the value 3 here, it would be 3 by 2 minus half, which is 1. And all other values for y greater than 3, it would be the value, it will take the value of 1. It is pretty straightforward here. So this is what the cumulative distribution function of y looks like. Now if I want to find out the probability density function of y, all I need to do is I need to differentiate it with respect to small y. So I'll differentiate the CDF of y with respect to small y and I'll get this. So from the range 0 to 2, it is y square by 2, and if I differentiate it with respect to y, I would get, sorry, it was y square by 8, and if I differentiate it with respect to y, I would get y by 4. And for the range to where y lies between the range 2 to 3, it is y by 2 minus half, and if I differentiate it, I will get the value half. So I can say the PDF of y looks something like this. It goes from this value y by 4, where y lies between 0 and 2, and it lies it stays constant at half, where y lies between 2 and 3. So you can say that it looks like this. So this is small y, this is the probability density function of y, where it increases linearly from 0 to 2 with the slope of 1 by 4, and then it stays constant till the value of 3. You can also verify that this area under the graph, the value of this area is 1, as the value of this rectangle is half, and the value of this is also half. So half plus half is 1, and it satisfies the conditions of the probability that the total probability should be equal to 1. Hence we have found out this probability density function of y and the cumulative distribution function of y where y is a function of the random variable x. So I hope you like this video. Thank you for watching.